Well, it's time for Wise Guys Wednesday.
That's right. U of I physics professor Paul Kwiat is joining us this morning for part 3 of our lesson about the notebook.
The amazing conclusion. Okay, so as you remember, the point is that other wise guy, Matt Sellens, gave me this notebook to try and explain how it worked. And it's got this, if we zoom in on it, it's got this amazing kind of, well, I won't say holographic, but thing that looks like it's discs and they're like mirrors and
possibly 3D, but not.
3D, right? And so I thought, well, this would be a way of thinking about the scientific method and how we actually solve problems. And so the scientific method, if we just put up that other slide, is that we have some question that we want to solve, and then we do some background research, and I tried to figure out where it was made, and I couldn't really get any information about what it actually was. And then we have some hypothesis. We do some experiments to try and look at it, and then depending on whether there are experiments support our hypothesis or not, then we may have to go back and keep trying again. Okay, so when I started looking at this then, I thought, well, there are a number of ways that I know that I can make images with things. I can make images, in fact, actually, if we just put up the other slide, I can get images either with lenses and refraction, or with reflection, like with curved surfaces, or with diffraction. Which is this thing where you have lots of little patterns that scatter the light, basically, and a wave-like property. And then, so if we just come back to this, we kind of went through each of those, and we said that, well, okay, it can't really be refraction or reflection because those require curved surfaces, and this is a completely flat thing. And then we said last time it can't be diffraction because if it's diffraction, that's wavelength dependent, and then all the images would be colored, basically, which is works for all colors. So then we come back again to our scientific method, and we realize that, okay, now we have to do something different. We have to reassess our basic assumptions, because one of the basic assumptions was actually wrong in saying what we previously said when we crossed off one of the other things, because those are really the only ways to make images. So somehow I've crossed them all off, unless they can't all be wrong, because one of them is actually doing this.
Of course.
What do we do?
Okay, so back to me. So I'm going to pull out this other thing that we've discovered. Yes.
Oh my gosh, that's awesome.
Yes. So it's a it's a big lens.
That's awesome.
But it is a completely flat lens.
Yes.
Okay. So the thing is that lenses actually don't necessarily require thickness. The way that they work is they have angles. So if we go to my next slide, which had how imaging works, so I've got light in the top that's going through a lens, and because it's bending at the interface, it gets focused down to a point, for example. If on the other hand, I just have a parallel slab, that doesn't really bend the rays. So the rays coming out the right-hand side are the same as the rays coming in the left-hand side. So if we go to our next slide, then you could take a lens, which is shown on the left, and the lens has this curved surface, and then it's got a bunch of flat regions that are lifting them up. And if you imagine removing all those flat regions, then you would get something that looks like the image that's kind of in the middle, that just has the grooves at different angles, but you've removed all those parallel slabs, and you get something that's then basically flat. And in fact, this was invented by Fresnel to make lighthouse lenses, because they need really big lighthouse lenses, but you can't make really thick glass. It'll just sag under its own weight. So instead, they cut out all these other regions, and that's what this is. Okay, so now I took this to, we have a wonderful analysis lab, and I put up my next slide, and they did a very careful analysis of what this thing looks like, and basically showing that it's got those little grooves, just like I was saying, and they're pretty small. They're only like 20 microns high or something. And then the question is, that actually explain what this is? So if we now put up the next slide, which is doing the same analysis on this, in fact, it has exactly the same sort of grooves. They're very small. They're only like 10 microns high, and your hair is like 100 microns thick. So they're very, very small. That's why this can be completely flexible and very thin.
That is so cool.
Mystery solved. Mystery solved.
Paul,
I love it.
That's great. Can you put this in front of your face one more time?
I was just going to say that.
Yeah. Can we get a shot of this happening right here, over here?
This one.
Camera 4.
Over this one, okay.
Okay, do it. Kind of go in and out. There we go. Very cool. Thanks, Paul.
And they have these like on the back of vans. You might have seen sometimes.
Yes, I haven't, but I believe you.
Yeah.
Awesome. Thanks, Paul. Thanks for solving the mystery. Thanks, and you know, always send people your questions. Our Matt's, Nadia, Paul, Jeff. Obviously, Paul. But yes, you're always looking for questions, correct?
Always looking for new things to look at.
Always. Well, thank you so much, Paul.
Thank you, guys.
Of course.
And still to come on the morning show, we took on the challenge of the lab escape.
You're going to see how we did and the challenges that we were facing, and Paul's going to talk with us. That's coming up.